Okay, this is the second part of lecture vibration. It's called free dam vibration for mechanical system. And you have a model with mass, spring, and damper, like here. Then you use free body diagram to derive the equation in the form of differential equation. Here you can see before, but let me clarify at this part. How can you have this equation that the right hand side is 0? It means one, you attach the mass m to the spring and the damper, and you hold it and release it slowly until it reaches the equilibrium. Yeah, when it reaches equilibrium um, here, then you can release it. Then it does not have any motion. Okay. Then you label the h, the scale 0 at here, point 0 is here. Okay. So it starts 0 from here. After then, you pull it a little bit to have h0, which is not 0. You pull it and then you release it, and it will vibrate. Okay. And the vibration is governed by this second order differential equation. And the right hand side is 0, then you can just analyze the homogeneous solution. Okay? You don't need particular solution. Um, the idea is to find this solution is to assume that the solution is exponential form, which have the same form of the derivative as first and second and so on. Then you got characteristic equation after you substitute the h to here, and you find h dot first, and then you substitute there, and then you find h double dot and you substitute here. If once you got characteristic equation, then you can find its roots. Okay, so the roots you use delta, and then you find s1 and s2. This is the square root of delta. And if delta is positive, well, here it's still the general form. Okay, not explaining about the sign of delta. Yeah? So this is just general form. So next, if delta is positive, which means you have this term greater than this term, yeah? And it's called overdam. Okay, overdam here. And if this delta is negative, which means this term less than this term, the response has complex number, and the complex number part is this. Okay, and this case is called underdam. And if delta is 0, which means this term equal to this term, and is the special case between the oscillatory and non-oscillatory motion. Okay, and this case is called critically damped. Critically damped, and denoted by critically damping C sub C. And omega n is called the natural frequency. So for undamped system means C is 0, then you have only spring and the mass. Then the oscillation is oscillate forever. and the frequency of the oscillation is called natural frequency, denoted by omega n here. Okay, then if you use a standard form that has this form, okay, this standard form. So you have damping ratio zeta, and you have natural frequency omega n. And here is the general solution written with zeta and omega n. Okay, so you have exponential term, and then exponential term of the number which is always real, and exponential term here, the number here can be real or complex number depending on the value of zeta compared to 1. So you have the most interesting case, because vibration means the motion is oscillatory. So the most interesting case is underdamped with zeta less than 1. And the form of the solution is like this. Okay. So you have exponential term here. If you use the rule of characteristic equation S equal to sigma plus j omega d, then sigma is minus zeta omega n. Okay, and omega d is omega n square root of 1 minus zeta square. So here is exponential of sigma t, and here the complex term, with the complex conjugate a and b here, then finally you only have real number, real function, sine and cosine, and you can have the general equation like this. So sometimes you can see this one is cosine, and you use here is as a theta. But if you want to write it as a sine function, you just choose phi equal to theta plus pi over 2, right? Theta plus pi over 2, right? So it means you have sine of omega dt plus theta and plus pi over 2. Then you can have cosine omega dt plus theta, correct? Yeah. So don't worry, sometimes you can see you see the sine function, sometimes it's cosine function. You can always transform from one to another. And look at let's observe the motion of the system. So at the initial time, you pull the mass to the distance h0, here h0, okay, and then you release it. look, it's why it's become larger. It should be, it becomes smaller and then oscillate. So yeah, this is if you well, if you just look at the function itself, you can easily draw it, and it depends on how you choose phi. If you choose phi as um, 0, no, if you choose phi as pi over 2, yeah, if you choose pi over 2, phi as pi over 2, it means the x-axis should be here, the axis should be here. Yeah, that's what I'm trying to say. If I want to compare it to the motion of the mass spring damper itself, right? But here the graph here, it does not care about how you match with the motion of the spring. You start from V0 from somewhere, and then, but here it just explain how you can draw the curve of this function. Okay, once you choose phi. Okay, but if you want to match the curve to the motion of the mass spring damper, then you need to choose phi properly. Okay, it's just like that. Okay, now let's just see the terminology. Okay, the terminology in here. For example, the period TD here, period here represent the period of the of the sine function. Okay, so it means yeah, it means 2 pi divided by omega d. Here omega d, right? 2 pi divided omega d is the period. You can so the period from peak here to peak here. Okay, um, what else? This curve is called the envelope curve. Where you get this envelope curve? Actually, this envelope curve is the exponential term itself. Okay, the exponential of sigma t. With the amplitude h, yeah, like this. So when t is 0, the exponential become 1, then you start from the value h here. Okay, so you have envelope like this. If you don't have the exponential term, you have h, you have a straight line like this, and you oscillate, okay, from minimum to maximum like that. Okay, but when then you have exponential term, and this term can be considered as amplitude of the sine function as well. That's why you have the exponential curve representing the amplitude of the sine function, so that the oscillation of the sine function is within the envelope curve. Okay? You can imagine that way. It can be easily remembered. And omega d is called damp frequency. And yeah, tau d is called period of the damp vibration, and measured in seconds. Frequency omega d is measured in the oh, I think this is not right. This should be radian per second. Okay, radian per second. Yeah, anyway, radian per second and hertz is just different by the factor of 2 pi, right? 2 pi f, and f is hertz. Okay, hertz is 1 over second. The next case, critically damped. In the case of zeta equal to 1, or you can say c equal to this, then the general solution, it looks like this. In this case, there's no oscillation, so the curve is just like this one. You can see here, just like this, and then go to, yeah, like this, go to this one. And the last case, overdamp. Overdamp means when the mass fall, oh, you pull it, and when you release it, it just go up slowly to the equilibrium point and stop there, like that. So the bigger the damper, the slower it moves. Okay. So this one is overdamp. Okay. So you can see here the behavior of second order system on the homogeneous solution is much similar, yes, similar to the second order system that have homogeneous and particular. It just where you start is different. For in the case of the system that has input, you usually you start from 0 and then you reach somewhere. But for this one, you do not have the input because this free damp vibration. It means you don't have external input. That's why when you put the mass on the system, you hold it and release it slowly until it reaches the equilibrium first, to let the initial extension of the spring cancel out with gravity. After then, you pull it to a certain h, the initial h, you call it h0, and then you release it to let it vibrate freely. That's why it's called free vibration. So where you start is different in this case. You always start from not 0, because in the free vibration you don't have input. If you don't start, if you start from 0, it's always 0. I mean, if you start at the equilibrium point, it's always there. It's always stay at the equilibrium point. So for freedom vibration, you must start from somewhere which is not 0. Okay. So let's just review from the first case, underdarm that has oscillation, this one. Yeah, the oscillation decay, this one, see, oscillate, and at the same time it decay until finally it's just stay at the equilibrium point, which is 0 displacement on the x-axis. And for undamped, this one, the black one here, for undamped, it means if you pull out, you take out the damper. Once you start, you pull the initial is 0 to a certain distance, displacement, and you release it, then it vibrates forever, oscillate forever, like that. Well, this is the illustration of the root of the real characteristic equation. The characteristic equation can have real root or complex root. Then you can see here it's complex plane. Okay. Complex plane. So you have real axis, imaginary axis. In the case of zeta greater than or equal to 1, the root S1 and S2 always on the real axis like this. Okay. So at this point, when zeta equal to 1, omega n equal to 0, because there's no complex part. There's no imaginary part. Omega n is 0. Look. Zeta equal to zeta equal to 1. Oh, yeah, omega is still there. Sorry. Omega this is still there. Zeta equal to 1, and you have a double root. Double root, and the double root is equal to omega n. Yeah, but there's no imaginary part. Imaginary part has the term zeta square minus 1, but zeta equal to 1, then this is already 0. Yeah. So the real part is minus zeta omega n. So when zeta is 1, then the double root here is minus omega n. And when zeta less than 1, you start the root of the characteristic equation start to drift away from the double root that it has complex conjugate. If you have one complex number there here, you must have one complex number here. Always symmetric with respect to the real axis. Okay, always symmetric. Because for the root you always have plus minus square root of delta, right? You always have this. So if this one become complex number, this term just appear one up there and one down here. Always symmetry. Okay, that's why we say for the root of second order polynomial always, yeah, if it is complex number, if the roots are complex number, they must be always complex conjugate. Okay? The complex part, one is plus there, the other one is minus, okay, which is symmetry. Here there are more terminology. Yeah, it's called logarithmic decrement. Yeah, actually, it's just to simplify the scale of exponential. Because for example, here the ratio of the ratio of the real part, exponential of the real part, and exponential of yeah, again real part, but at different time. I mean the ratio of h2 here, h1 and h2. Yeah, h1 here, h1 and h2. Okay, the ratio. The ratio here represent the ratio of the maximum, local maximum from one to another, with the period td, uh, not t but tau, yeah, tau d. So just want to compute this ratio. So yeah, compute this ratio and uh, take the logarithm to eliminate the exponential term. And finally, you just have this term, zeta omega n times tau d. Okay, and here is tau d, tau, yeah, period is 2 pi over this. Okay, so finally, for small value of zeta, yeah, this is approximation. For small value of zeta, um, this one just approximately 1. So finally, the ratio is approximately 2 pi zeta. Okay, so the ratio from the peak of, uh, yeah, from one peak to another peak with the period tau d can be expressed by this. We call it logarithmic decrement because it's decreasing from this to this and then from this to this. Okay, so in logarithm, the logarithmic decrement are the same. Okay, and approximately to be this value. Okay, the most terminologies for vibration are illustrated in this lecture. So that's all for the second lecture of vibration. You have any question? No?